In this lecture, let us discuss infinite impulse response filters, IIR filters. So let us discuss first low pass filter and then followed by high pass filter. Okay, so now we will see how it is derived from a very common sense. If you recall that 1 plus C inverse, what is this? This is the low pass filter, FIR low pass filter, if you recall. Okay, so this is an FIR low pass filter, finite impulse response low pass filter. Now we want an IIR filter. That means what? The impulse response is infinite. Okay, it has infinite number of impulse response. Okay, that's what we mean by IIR. Like you have h of z, take inverse z transform IZT, you will get h of n. This h of n contains infinite number of samples. For example, if I say h of n is equal to 1 by 2 whole power n into u of n, then you have, when you substitute n is equal to 0, then you will get 1, n is equal to 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16 and so on and so forth. So this is the example of infinite impulse response filters. Okay, so for FIR filter, this is finite response, finite impulse response. Why is it finite impulse response? If you take inverse z transform, then h of n is equal to del of n plus z inverse is del of n minus 1. Simply it has only 2 samples, finite impulse response. But on the other hand, if I take h of z equal to 1 divided by 1 minus z inverse, then this is going to be u of n. It has so many samples. Now let us see how one can derive this infinite impulse response filters from the finite impulse response filter. Now as I said, 1 plus z inverse is the low pass FIR filter, finite impulse response filter. Now we want an IIR filter. Therefore you must add a pole. Okay, so pole means the denominator. So let the pole be at alpha. This is alpha. As I said, pole is denoted by a cross symbol like this, and 0 is denoted by a small circle. We add a pole at z equal to alpha. Therefore 1 minus alpha times z inverse, the denominator. Now if you take this on the whole, then this is going to be IIR filter, infinite impulse response filter, and this is the simplest filter. If you plot the poles and the zeros, then you have a pole at alpha and a 0 at z equal to minus 1 in this point. This is a 0 and this one is pole. Okay, so we have introduced a 0 at z equal to minus 1, and we have introduced a pole at z equal to alpha. If you take alpha as a real positive quantity, then this is your pole. But obviously for stability, alpha is whether real or complex or positive or negative, the magnitude of alpha must be less than 1. That means what? Poles must be inside the unit circle. Okay, now my h of z is equal to 1 plus z inverse divided by 1 minus alpha times z inverse. This is the FIR filter. Now I need to normalize the filter. That means what? We normalize the DC response to 1. Normalize DC response to unity. What does it mean? When omega is equal to 0, my h of e to the j omega is equal to 1. That is called a normalization. Okay, that means omega is equal to 0. This implies z equal to 1. Okay, so in this, if we substitute z equal to 1, then h of 1 is equal to 1 plus 1 divided by 1 minus alpha. So this is 2 divided by 1 minus alpha. Okay, so now I need to make this guy to unity. How could I do that? You multiply by I want to make this 2 by 1 minus alpha to unity. What shall I do? If I multiply this guy with a factor of 1 minus alpha by 2, then I'll get unity. Therefore, in this function, let me multiply by 1 minus alpha by 2 times 1 plus z inverse divided by 1 minus alpha z inverse. So this is your normalization factor. Okay, so this is my h of z now. Now if we substitute z equal to 1 in this, h of 1 is equal to 1 minus alpha by 2, 1 plus 1 divided by 1 minus alpha. 1 minus alpha will get cancelled, and this 2 and that 2 will get cancelled, is equal to 1. Therefore, z equal to 1 means what? DC. So that DC response is normalized to 1 now. Therefore, my low pass filter is infinite impulse response low pass filter is 2 divided by 1 minus alpha divided by 2 1 minus alpha divided by 2 1 plus z inverse divided by 1 minus alpha times z inverse. So this is the IIR low pass filter. So why do we need this? There's a multiplying by this to get h of z equal to 1. Okay, and this is the scaling constant. Why did we introduce the scaling constant? Because to make DC response to be unity. For that reason we are introducing that. Therefore, what is a DC response? DC response is 2 divided by 1 minus alpha. Okay, so and we normalize this 2 minus alpha. Where is it? Yeah, it's here. We normalize this 2 divided by 1 minus alpha to 1. So my simple IIR low pass filter becomes 1 minus alpha divided by 2 multiplied by 1 plus z inverse. In the denominator you have 1 minus alpha times z inverse, and this is the simplest possible first order low pass IIR filter, IIR digital filter. Why is it IIR digital filter? Because if you take a inverse Z transform, then you'll get h of n. That h of n contains some factor like minus alpha to the minus alpha or plus alpha. You can check it out. Whole to the n into u of n, like that you'll get it. Some factor will come like this. Therefore, you substitute n is equal to 0, n equal to 1, 2, 3, 4, like that. It has so many samples: alpha power 0, alpha power 1, alpha power 2, like that. Okay, so that is why this is an IIR filter, infinite impulse response digital filter, and this is the simplest possible first order low pass filter. Now, well, we want transmission at low pass filter means transmission at z equal to 1, that is at omega is equal to 0, and this is satisfied by the numerator. In the numerator I have 1 plus z inverse. Anyway, this will satisfy. Okay, because 1 plus z inverse is a low pass filter, FIR low pass filter, so we don't have to bother about the numerator. So in the numerator wise, no need to worry. 1 minus alpha divided by 2, 1 plus z inverse divided by 1 minus alpha times z inverse. So the numerator, nothing to worry. But what about the denominator? Okay, so if you put z equal to e to the j omega and then find out the magnitude response. So h of e to the j omega is equal to 1 minus alpha divided by 2, 1 plus e to the j omega it is z inverse, right? So e to the minus j omega divided by 1 minus alpha times e to the minus j omega. Now use Euler's identity. So 1 minus alpha divided by 2, 1 plus e to the minus j omega can be written as cos of omega minus j times sin of omega divided by 1 minus alpha times cos of omega minus times minus plus. Is it correct? Yes. Plus j times alpha times sin of omega. This is h of e to the j omega. Now you take magnitude of this, okay, and square it. You will get 1 minus alpha by 2 the whole squared, and in the numerator 1 plus cos omega whole squared plus sin square omega. The denominator 1 minus alpha cos omega whole square plus alpha squared sin square omega. Is that right? 1 minus alpha the whole square divided by 4 times, expand the numerator, 1 plus cos square of omega plus 2 cos omega plus sin square omega divided by 1 plus alpha square cos square omega plus 2 alpha minus 2 alpha cos omega plus alpha square sin square omega. If you simplify this, 1 minus alpha whole square by 4, in the numerator you will be having 2 plus 2 cos of omega, in the denominator 1 minus 2 alpha cos omega plus alpha square. This is the magnitude of the filter. Now if you plot this magnitude square, okay, magnitude square plot this magnitude square characteristic, you can show by differentiating this guy that the magnitude response is monotonic. That is, differentiation of by d omega with respect to d omega is less than 0 in the range of 0 and pi. Okay, therefore this condition ensures that the function h of e to the j omega is monotonically decreasing. Monotonically decreasing means, as I said, at omega is equal to 0, its value is 1, and then it monotonically decreases like this, and it reaches 0 when omega is equal to pi. Okay, so that means it falls monotonically to 0, from 1 to 0. Okay, and here the parameter is alpha. Unlike the FIR, the simplest FIR, which was, what is the FIR? 1 by 2 times 1 plus z inverse, right? What is the cutoff frequency here? The cutoff frequency was like pi by 2, but here the cutoff frequency can be controlled. In FIR case, you can't control. You can't control the cutoff frequency, but here can be controlled by using alpha. Okay, using the parameter alpha. Therefore the cutoff frequency can now be controlled by alpha, and if you plot the characteristic, it will be like this. It will be like this. And then if you increase the alpha, then the characteristic will go like this, and again if you increase alpha, then the characteristic will go like this. Therefore this is a direction in which your alpha is increasing. Okay, alpha increases in this direction. That is, as alpha increases, the characteristic becomes better and better. In fact, you can show that the 3 dB cutoff frequency, how do you find the 3 dB cutoff frequency? By equate the magnitude to 1 by root 2. Okay, so the maximum is 1. So you equate 1 by root 2. You take h of e to the j omega and the magnitude you equate to 1 over root 2. If you do that, then 1 minus alpha whole squared by 2, 1 plus cos at cutoff frequency, right, cos omega c divided by 1 minus 2 alpha cos omega c plus alpha squared is equal to 1 by root 2. Okay. Okay, so I'm writing this expression, okay, and notice here the expression is magnitude squared. So then I'm equating h of e to the j omega magnitude is equal to 1 by root 2. Then what about the magnitude square? Square is equal to, so square on both sides, it become 1 by 2. So that is why this expression is equated to 1 by 2. Okay, now simplify this. Do the cross multiplication and I mean simplify this expression, like expand this. 1 minus alpha whole square becomes like you take this 2 here, 2 times 1 plus alpha square minus 2 alpha divided by 2, 1 plus cos of omega c. At cutoff frequency the magnitude is 1 by 2, 1 by root 2, but if you square it, it becomes 1 by 2. In the denominator, 1 minus 2 alpha cos omega c plus alpha square is equal to 1. Simplify this. Finally, you will end up with cos omega c equal to 2 alpha divided by 1 plus alpha square. So this is the cutoff frequency. Now omega c is controlled by alpha. Okay, so what is omega c? Omega c is the cutoff frequency, and this cutoff frequency is controlled by omega c. So controlled by alpha. Okay, so if you are asked to design a filter with a given omega c, there is nothing else you can, given omega c, then there is nothing else you can control, only one parameter alpha, and therefore you can only control omega c. So if omega c is given, then to find out alpha you have to solve this quadratic equation, 2 alpha divided by 1 plus alpha square. Therefore cos omega c is equal to 2 alpha divided by 1 plus alpha square, and then if you cross multiply this, you will get alpha square cos of omega c plus cos of omega c plus 2 alpha is equal to minus 2 alpha is equal to 0. It's a quadratic equation in alpha square. You solve this, and once if you solve it, then alpha is equal to plus or minus alpha is equal to 1 plus or minus sin omega c divided by cos omega c. It is a very simple calculation, straightforward calculation. Okay, this is like ax square plus bx plus c in this formula. Okay, you know this quadratic equation solution, where a is equal to cos omega c and b is equal to minus 2 alpha and c is equal to cos omega c. That's it. Substitute minus b. What is the root? Minus b plus or minus square root of b square minus 4ac divided by 2a. This is your alpha. Once you do this substitution, then you'll get this answer. Okay, so therefore alpha is equal to 1 plus or minus sin omega c divided by cos omega c, and it turns out that 1 plus I'm sorry, this is common like that 1 plus sin omega c divided by cos omega c is a quantity which is greater than 1. And similarly 1 minus sin omega c divided by cos omega c turns out to be less than 1. And therefore acceptable alpha is equal to 1 minus sin omega c by cos omega c. Acceptable alpha, because I can't take more than 1. If I take, then it will give some problem. Let's see what that problem is. 1 minus cos omega c. So this is the simplest IIR low pass digital filter. Now in case if omega is equal to omega c equal to pi by 2, then what is your alpha? Alpha is equal to 1 minus sin pi by 2 divided by cos of pi by 2. So I'll get 0 by 0. So use L'Hospital rule and then differentiate numerator separately and differentiate denominator independently. Then the numerator becomes cos omega c, denominator becomes minus sin omega c. Minus and minus will get cancelled. Now you substitute omega c equal to pi by 2, then it is cos pi by 2 divided by sin pi by 2. This is 0. Therefore alpha is equal to 0. If alpha is equal to 0, then what do you get? You simply get, what is my h of z? H of z equal to 1 minus alpha divided by 2, 1 plus z inverse divided by 1 minus alpha times z inverse. In this expression, if you substitute alpha is equal to 0, then what will you get? You will get 1 by 2 times 1 plus z inverse. What is this? This is simply an low pass FIR digital filter. Okay. Therefore, if alpha is equal to 0 corresponds to omega c equal to pi by 2. You don't need an IIR filter, and you will get FIR filter, and that's the job when alpha is equal to 0. Okay. If omega c is equal to pi by 2, you don't need an FIR filter. Okay, a simple FIR filter does the job. Now let us move on to high pass filter. High pass IIR digital filter. Okay, and I told you that in general in a low pass filter change z to minus z, then you'll get a high pass filter. Okay, so you change z to minus z, you should get a high pass filter. Therefore, what is our low pass filter? H LPF z is equal to 1 minus alpha divided by 2, 1 plus z inverse divided by 1 minus alpha z inverse. Now I need a high pass filter HPF. You simply replace z by minus z, 1 minus z inverse divided by 1 plus alpha z inverse. Okay, so it will indeed be a high pass filter. Okay, suppose I want to keep the pole at the same place, z equal to alpha. Now what is the pole location in this? The pole is located at minus alpha. Okay, so the pole is located at minus alpha. If you take the low pass filter, where was the pole? The pole is at plus alpha. If you look at, yeah, see, the pole is at plus alpha. Now once you move from, once you replace z by minus z, then the pole is moved to this negative axis location. In case I don't want the pole to be located at minus alpha, I want the pole at this place, alpha plus alpha itself. What shall I do? Okay, here the pole is shifted to plus minus alpha. Okay, this pole is shifted from z equal to alpha to z equal to minus alpha. Suppose I don't want that. I want the pole to be at the same place, but I know if I want a high pass filter, the numerator must be 1 plus z inverse. Sorry, the numerator must be 1 minus z inverse for high pass filter. So I can't do anything in the numerator. Okay, let it be as it is. So all that I have to change is the multiplying constant. Okay, so therefore change alpha to minus alpha in this expression. So that what is going to happen? It is 1 plus alpha by 2 times 1 minus z inverse divided by 1 minus alpha times z inverse. Okay, so this also high pass filter HPF of z. Either you can consider this expression, this is correct, or this also correct. What did I do from this expression to this expression? Simply I changed alpha by minus alpha. Why did I do that? Because I don't want to keep my alpha at this location. I need to keep in the same place. That is why what did I do? I simply replaced alpha by minus alpha in this expression. I get this one. Let me call this is 2 and this is 1. 1 and 2 are the same, one and the same. Equation 1 and 2 both represents an IIR high pass filter, digital filter. Okay, so either you can use 1 or you can use 2. Okay, either of them are acceptable high pass filters. Okay, now let's consider this one, the equation number 1. So high pass filter z is equal to 1 minus alpha divided by 2 1 minus z inverse divided by 1 plus okay, let me take equation 2. 1 plus alpha divided by 2 1 minus z inverse divided by 1 minus alpha z inverse. Okay, maybe let me drop the subscript, not needed, or let it be, no problem. Now the magnitude characteristic h of z versus omega would be just the complement of low pass filter. For low pass filter it was like this, right? Like this. I just take the complement of this, then it is going to be like this, like this, like this. If you take magnitude like this, and this point is pi. Now if you vary the alpha in this direction, if you increase the alpha, then your curve will move in this direction. This is for alpha 1 and the second curve is for alpha 2 and this curve is alpha 3, where alpha 3 is greater than alpha 2, alpha 2 is greater than alpha 1. So if you increase the alpha, the curve moves like this, it becomes more and more ideal. Okay, so the alpha increases in the upward direction. As alpha increases, the characteristic becomes better and better, more and more ideal. See, initially it was like this, and then it became 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 like this and like this. What is your ideal high pass filter? Ideal high pass filter will be like this. So when you increase alpha, it becomes more and more ideal. Okay, more and more approach towards the ideal. See, my ideal high pass filter will be like this. If alpha is equal to, let's say, 0.1, then it will be like this. Alpha is equal to 0.2, it increases like that. When alpha becomes 0.4 or something, like, just as an example I am telling you this, and then you take alpha is equal to 0.5 or 1 like that, then it keep on increases. This is for alpha is equal to 0.1, this is 0.2, 0.3, this may be 0.5, I don't know. So if you increase alpha, then it approaches towards the ideal characteristic. Again, once again you can put in this expression z equal to e to the j omega. Okay, and you can find out the magnitude response and find out the cutoff frequency. Okay, so it is a simple straightforward exercise. 1 plus alpha divided by 2, 1 minus z inverse divided by 1 minus alpha z inverse. Then substitute z is equal to e to the j omega. So h of e to the j omega is equal to 1 plus alpha divided by 2, 1 minus e to the minus j omega divided by 1 minus alpha e to the minus j omega. Same exercise what we did earlier. And then you take magnitude square, then this is 1 plus alpha divided by 2 the whole square, and here I will be having 1 minus cos omega in the denominator, 1 minus 2 alpha cos omega plus alpha square. And then at cutoff frequency the magnitude is going to be what? 1 by root 2. Square this on both sides. So h of e to the j omega magnitude square is equal to 1 by 2. Equate this 1 by 2 to this guy. So 1 plus alpha by 2 the whole square, 1 minus cos alpha divided by 1 minus 2 alpha cos omega plus alpha square is equal to 1 by 2. By solving this, you will get once again cos of omega c is equal to 2 alpha divided by 1 plus alpha square. It's pretty straightforward calculation. So it turns out that the cutoff frequency is identical as in the previous case, low pass filter. For low pass filter also the cutoff frequency is 2 alpha divided by 1 plus alpha square, and for high pass filter also the same formula. Okay, so once again if you want to design a filter for a specified omega c, then you have to solve this equation and find out the alpha. See, omega c is given, but we need to know what alpha will give you this omega c. For that you have to solve this equation. So alpha is equal to 1 plus or minus sin omega c divided by cos omega c. As I said, plus will not give the acceptable value. Therefore we need to consider 1 minus sin omega c divided by cos omega c. This is my alpha. Okay, so you can do this algebra and you can solve some numerical examples. Okay, so you'll get the very clear idea. Okay, so that's all about low pass filter and high pass filter. So now the next comes the question of band pass filter. Okay, band pass filter, that we will discuss in the next lecture. Band pass filter and then band stop filter and then all pass filter. So these are the things that we will discuss in the next lecture. Okay, so let me stop at this point. Thank you very much.